Hello, this is Elijah Peters. This is our final project of data structures and algorithms. This project specifically is on a sorted linked list into a V-tree and implementation of 5,000 random numbers from a range of 1 to example 50,000 or 100,000. And let's start getting into some of the classes I created to separate the tree and sorted linked list. So if we're getting into the B-tree class, we have a B-tree node internal structure for the tree, having its keys, children, the leaves, and so the max keys is 2 times t minus 1, and the max children is 2 times t. And for the operations, there are adapted for descending order. The B-tree descends down from numbers. This is the insertion logic for the B-tree. And if k is smaller than the median, the s key is 0, it goes to the right child, which I equals 1, and it splits the full child y of the node x at index I. Then we copy the last t minus 1 keys of y or y to z. If y is not a leaf, copy the last t children of y to z, and shift children to x to make space for z. Then we get into the for statement for the for loop for shift keys of x to make space for the median key. We move the median key, which is y keys t minus 1 from y to x. Then we insert a key into a full or non-full node x. We find the location to insert the key, and it must maintain the descending order. We find the child where the new key should go in the descending order. And after they split, we check the newly promoted median key. We keep an in-order traversal for descending order, and we use recursion statement on the last child, just c, which is index xn, and we iterate backwards from last key, which is k n minus 1, down to k0. We append the key ki, and then recurse on the child ci, which is to the left of ki. And these are some of the search function implementations. So find the first key that's smaller than or equal to k for the descending order. The key k is found at index I. The key is not found, and this is a leaf node. Search the appropriate child, which is child I. Dynamically find the key in the root and a key in the deep leaf. The root key and the leaf key, and then descend to the rightmost deepest child holds the smallest value. And now if we get into the custom random Java, we get into the pseudo random number generator. And we use a constructor that initializes with all the starting values, and we ensure positive numbers are within the range of those values for the numbers, the random numbers. We get into data structure, or we get into the data structure project, and we see that in this one specifically, this class integrates the data generation, the sorted linked list, insertion sort, the B-tree construction, the traversal, and the search using the B-tree degree, which I chose of t equals 5, and maintaining descending order throughout. So getting into it, we have the constants configuration, we have the file operations and workflow to make each file for the data text and the tree traversal text. We have the data generation. When we get down here, we read the data and build the sorted linked list. And we get down to the B-tree construction. We have the B-tree traversal, printing out the traversal to verify the B-tree order, which will show up in a snippet. And we have the search functions, the demonstration, and for max plus 1 equals the missing value, which will show up at the bottom of the terminal when ran. It will show the the three keys, one missing, one at the beginning, one at the end. And it will show that out all printed out to the terminal. Now we get into the node Java, which is just the foundation of the singly linked list. It's just initializing the data and the next node, constructor for the node class. And if we get into the sorted linked list, we have this implements the insertion sort to maintain the descending order. First, we insert a new number maintaining descending order, empty list, or new data if it is greater than the current head. Find the insertion point, stop when the current next is null, or the next node's data is not greater than the new data. And then we print the first 20 and last 20 numbers using the 2-point approach, because the first pointer only gave the 2 first, and we couldn't find the 20 last numbers with such a large list without having an import. So it's great to have 2 different pointers, making less time finding those numbers at the end of the 5,000 list. It's such a far way away. All right, prints first 20 numbers, the largest, and then we find and print the last 20 numbers, the smallest, using a 2-pointer method. And then there's nothing more to print. We move fast pointer k steps ahead, move both pointers until fast hits the end, which is null. And if we run this, you'll see that it generates the 5,000 random numbers, range 1 to 50,000. The data text is created, updating the 5,000 numbers using the fixed seed, and then the building sort linked list, which the insertion sort in descending order. The linked list is built and sorted successfully, inserting 5,000 items. The sorted linked list snippet for the report, for the descending numbers, it shows the first 20 numbers, the largest, and the last 20 numbers, the smallest. And then we get to building the B tree, which the t equals 5 from sorted linked list. The B tree is constructed successfully, and then performing the in-order traversal to verify the B tree order, which the tree traversal text created with the descending B tree output. Then we show the demonstration of the B tree, or the search functionality, using the found keys. And we have the first key found in root, which is 25,363. We have the key found in the leaf, the candidate, which is the 32. And then we have the key that's guaranteed missing, which is out of its parameters, which is 50,001, because our range is 1 to 50,000. We're looking for numbers in between those. So, and then we have the search results. We have, as you can see, the root candidate is found, and the leaf candidate is found, but then the missing, since it's out of its parameters, is not found, 50,001. And that is our final. And